Building a robot in the real world is an unforgiving process. Every hardware iteration consumes significant time and capital, and a single error in control logic can destroy months of work in a fraction of a second. To bypass this physical bottleneck, engineers now start with a digital twin, a mathematically accurate copy of the hardware that allows them to test reality within a safe virtual sandbox. This virtual workflow relies on two distinct pieces of software. Gazebo provides the physical universe, simulating gravity and 3D space, while the Robot Operating System, or ROS, provides the behavioral logic. Today, we are going to build a virtual robot from first principles to see exactly how this simulation pipeline translates code into physical action. Brought to you by Royal Research. This dual-stack pipeline allows developers to identify critical failures in a risk-free environment, ensuring that early-stage errors result in a system reset rather than a total hardware loss. Every robot begins as a set of mathematical constraints. Before construction starts, we must define the mass, dimensions, and material properties of every component. In Gazebo, these raw physical properties are defined using standard XML code, specifically within URDF or SDF files. We construct geometry through specific tags. A link tag defines a rigid body. Setting radius and length creates a cylinder on the virtual grid. To assemble, a joint tag establishes the kinetic relationship, dictating how that wheel rotates relative to the chassis. This modular code structure allows for immediate iteration. If a wheel requires more clearance, updating a single line of text regenerates the model, bypassing the time required to machine new parts. The URDF document serves as the foundational blueprint, forcing mathematical parameters to occupy physical space and obey the laws of physics. A perfectly engineered physical body requires environmental awareness to function autonomously. To provide this, we mount virtual sensors, such as cameras and LiDAR arrays, directly onto the URDF chassis within the Gazebo simulation. Gazebo's physics engine simulates the trajectory of light beams as they strike virtual matter. When a virtual LiDAR unit is active, the engine calculates the time of flight for beams bouncing off obstacles and returning to the sensor. This generates a continuous stream of distance measurements. That data becomes the primary source of truth the robot uses to make navigational decisions. Simulated perception creates a precise data pipeline, translating the geometry of the virtual environment into actionable metrics. To act on those metrics, we use the Robot Operating System to manage the machine's behavior. ROS uses distinct computational scripts called nodes. A custom control algorithm running in a node ingests raw sensor data flowing from Gazebo. The algorithm processes that input, determines the next move, and sends an output command back to the virtual actuators. This architecture separates concerns. ROS manages the software logic, while Gazebo handles the physical execution of those commands. Because of this modularity, developers can test multiple navigation algorithms against the same model without altering the robot's physical configuration. ROS is the cognitive bridge that transforms raw sensory input into complex autonomous behavior. Once the structural and behavioral models are complete, the robot must face the unpredictable conditions of a real-world environment. Gazebo allows us to manipulate environment variables, such as volatile weather, heavy payloads, and severe terrain, to stress test the robot's resilience. We monitor performance metrics during these tests, such as speed and energy consumption. This graph shows the energy draw spiking as terrain friction increases, revealing the exact limits of the robot's current motor configuration. If a failure occurs, there is no physical debris to clear. Developers analyze the telemetry, adjust the ROS nodes, and reset the simulation to run the scenario again. Virtual stress testing ensures the robot is prepared for environmental challenges before a single piece of hardware is manufactured. This pipeline creates a unified development loop. URDF defines the structure, Gazebo simulates the environment, and ROS drives the cognitive logic. This digital approach allows a single validated model to be duplicated into a coordinated fleet, testing swarm behaviors without the overhead of physical units. Shifting the iteration cycle from the machine shop to the simulation environment reduces the frequency of hardware replacement and the associated costs of physical testing. Once an application is validated in the virtual environment, the control software can be deployed directly onto physical robotic platforms. By utilizing Gazebo and ROS, developers have moved past the constraints of physical prototyping, establishing a foundation for rapid and reliable robotic innovation.